Hello. Well, good morning, everyone. We're getting close to the midterm, and I hope that you are reading the notes and doing the homework and also working on your lab reports. So I wanted to tell you here that the notes I have uploaded the last chapter, which is chapter number 4. So we have 1, 2, 3, and 4. There is just one tiny thing that we need to finish about chapter number 3, and then today we'll try to cover most of chapter 4. Not everything, but all you need in order to solve the homework. Okay? I'd like to thank you to those that have helped me to find typos and mistakes in the notes. I have corrected those. Probably they are not in the PDF that it's on Canvas, but if you go to this web page, you'll see that all the changes are already there. So let's start talking about homework number 2. Okay, I want to make sure that you know how to solve that one, and then we'll continue with the lectures. Okay, so homework number 2, the first problem is about stress convention. What you have to do is you have to draw stresses on the 4 sides of this square to be positive for normal and shear stresses. So sometimes, we call this axis X, Y, Z. Some other times we call it 1, 2, 3. Some other times we call it I, J, K. So it's all the same. It's always a right-handed coordinate system, and you have to follow the order. And remember the right-hand rule. So this is index is number 1, middle finger is number 2, and the thumb is number 3. If you do this, you'll never get that wrong. So let's go to the solution of the first one. Here, something that we did different compared to what we have done in class is that I look at the axis, I oriented those axes with one of those pointing down. Okay? The arrow always tells you, the direction of the arrow tells you the direction in which the axis increases positively. So according to our rule, whenever we do a positive increment, like for example in this case delta x, on the other side of the face, in order to have positive stresses, the normal stress should be pointing against x-axis, shear stress should be pointing against y-axis. If you do a negative delta x, will be going in this direction, opposite to this arrow, then you have those pointing in opposite direction. And for the other one, here the only thing that changes is the direction of this axis, and now it's pointing down, but the fact it's pointing down doesn't mean it's negative. You see the arrow, you see the direction there, it goes positive in this direction. So a positive increment will be in this direction, and because of that, on this face, we'll have this one pointing down opposite to this axis over here, that one, and the shear stress pointing opposite to that one. Most times, you could follow the same rule and draw the 4 faces, but also you'll realize that if you have this one pointing in this direction, the other one should be in the opposite direction. Same with the other normal stresses, and same with the shear stresses, in order to have equilibrium in this element. This is kind of important because many times our definition of stresses and the sign depends on our convention, and some people use conventions that are opposite to what we do, especially in solid mechanics. But in geomechanics, we use this convention and we treat that as positive. And if you do in 3 dimensions, it's one step more complicated, but not too much. Any questions about this problem? I like that you're comfortable dealing with X, Y, Z, and also with axes that are called 1, 2, 3. It's the same thing. Okay? Yes, Mr. A1.
I think this is something that
Well, it's the same thing as we have done here. Positive will be always on the opposite direction of the axis after crossing, after going a positive amount. So it's the same as the normal stress. It's the same thing. Okay? Yes, Miss Lower. Yes. Yes, it's positive.
And then the one on the left side going down.
It's positive too. It's positive because of the convention that we have adopted. So this one is positive, and this one is positive too, because if you do a negative increment, if you go, instead of this, if you go this way with a negative delta x, then now it should be pointing in the same direction of the axis. That's positive too. Yes?
Should we just do it if it's on the same side of the axis, it goes in the direction of the axis, and if it's on the opposite side, it goes opposite?
I think you can say that. That would be accurate too, but I prefer to to talk on terms of a positive change. All right, everyone good with this one? Okay, let's go to the next one. The next problem is about, well, the first thing that you should do in order to solve this problem is to remember how to do matrix times a vector multiplication. That's the only thing. What you see over here are 6 equations. That's what you have. And it's just a way of summarizing those equations and making it clear on what are the constants which are on this matrix and what are the variables. But those are just 6 equations. And in this case, what you're asked to do is to apply an action, which is in this case an isotropic stress. Isotropic means the same in all directions, with no shear, and to find out what are the values of these strains. So the only thing that you have to do here is to replace those values of normal stresses by your isotropic stress. You know these are 0, and then you just do the multiplication. So the first linear strain L09-1 is going to be just this one times that one plus this one times that one plus this one times that one, and all here these are zeros times already zeros, those are zeros too. So what you get over here for L11 and L22 is an equation that looks more or less like this. Notice the 1 comes from here, the -2 Poisson ratio comes from over there, and the common denominator was the Young modulus, and this is multiplies everything. So all the strains are the same. And this, the second jack from the, or the one closest to me. You got it? Oh, no. That's the power. Don't worry. Yeah, it's on this side. Okay. So it makes sense here that because we have an isotropic solid, which means that it has the same properties in all directions, that the strains are going to be the same in all directions too. So if you apply stress, which is the same in all directions, the strain should be the same in all directions too. And they're all the same, and we know that the volumetric strain is going to be the summation of those 3. If you add those 3, then you get 3 times that, and if you look at this as a constant, you get what is called the bulk modulus, which is just the inverse of that value. So this is k minus 1. The definition of the bulk modulus is this. The strain that you will get is the isotropic stress divided the bulk modulus. The second part of the problem is to state what is the stress tensor and the strain tensors. And what I want you to do here simply is just to write this matrix, to fill up this matrix with the current state of stress of this problem. In this example, we have no shear, so the off-diagonal terms are 0, and the diagonal terms are all the same, so all normal stresses are the same, sigma iso, sigma iso, sigma iso. And in the case of strains, there are no shear strains, so all off-diagonal terms are equal to 0, and diagonal terms are each of these linear strains, and they are all the same. So remember, the only thing that you have to do here is, given an action, just to find what are the effects of that action, which are, in this case, you apply stress, you get the strain, according to this constitutive law. And then everything you have to do later is just add those up in order to get the volumetric strain, and you get a solution. Any question about this one? Let's go to the next one, which is a little bit more complicated, okay? But remember that here you have stresses in all directions, you have strains in all directions too. Yes, Mr. Awa? No, you shouldn't memorize that. So I got a question before, which are the questions I'm going to give you. The questions I'm going to give you are the same that I'm giving you in the practice exams, okay? So you will see there that those are the questions, and you don't have to memorize this matrix. Yes, Mr. Wang.
So you're saying the strain 1, 2, 1, 3, and 2, 3 are 0 because we don't have shear stresses?
These ones?
Yes.
Yes. Because you don't have shear stress.
So if we only had a stress in like 2 directions instead of all 3, will we then have strains in the 2 directions?
Well, that's the next problem, okay? That's the next problem. So let's go to the next problem. The next problem is you have to utilize the same matrix. Well, it's the same relationship. It's just the other matrix. But notice here that there is a subtle difference here. Here you know that you're applying stresses and you want to calculate strains, okay? So you use this matrix that here you're, compare this to y as a function of x, okay? Here your x is what you know, the stresses, and you want to calculate the value of your function, which will be y. In the other example, you are applying a stress on one direction, but then you assume that as just being a strain, because you also know that there is no strain on the other 2 directions. So you know the strains. What you want to calculate are the stresses. That's what you don't know. Here you know that there is no strain to the sides, that there is just one strain in this direction. You do not know what are the stresses. So in this case, our unknown are the stresses. The known variable is strain. And you do the same that you did before. So in this example, there is no lateral strain, epsilon 22, epsilon 33. There is no shear strain, and there is a strain in epsilon 1, in this direction, direction 1. You do the math. We already did this in class, and you will find a relationship for sigma 1 as a function of epsilon 1, which gives you the constraint modulus. One thing over here, check your class notes or your lecture notes, and I did 2 mistakes in this matrix in class. Okay, so don't get confused. In the notes, in the web page, it's okay, and the PDF too. But in class, I wrote here a Poisson ratio instead of 2, and I wrote a positive sign instead of a negative sign. So check this matrix that in your lecture notes, it might be wrong, okay? So don't let that get you into the wrong direction, into the wrong solution of the problem. So let me find that. Okay, so this one over here, you see that you can see that I erased. There was a Poisson ratio there before, here, there, and there, and also here there was a plus sign. It should be a negative sign. Okay, so then you just do the math, and you use the other equations. For this one, you just use the top equation. For getting sigma 2, you use the other equations, and you replace sigma 1 or epsilon 1 in terms of sigma 1, and then you get the value of the stresses in this direction caused by a stress in that other direction. Try to do the following. This problem can get one step more complicated, you know. What about if you were to apply stress in one direction? It is constrained on this direction, it can move, but on direction 3 it's free to move. Try to solve that one. See what you get. Okay? That would be, you know, one more step in complexity of solving this kind of problem. And it's not just a thought experiment, but actually it has an application that's going to give you what is called the plane strain modulus that we use in this equation over here. Okay, any question about this problem? Remember, the first thing to do is to know how to multiply a matrix times a vector. So it's rows times column. Row times column gives you this. Second rows times columns give you that. Third row times the column gives you this, and so on. And then to know what is what you know, what is what you don't know. You could still solve the problem going the other way using this one, but it will be just a little bit longer. But you could solve it though. So if you did in the homework the other way, you will see that you get to the same answer. The tensors of stress and strain for this case. And now it gets more interesting, because notice that we have stresses. We have no shear stresses, but we have normal stresses. We have sigma 1, which is, let me write it again over here. This was our rock, and we had 1. Let me see, is this 1? This is 2. This is 3. So if we have stress in this direction because it cannot expand on the direction 2 and 3, we have sigma 1. We have a non-negative stress in direction 2. We have a non-zero stress in direction number 3 because it's constrained in direction 2 and direction 3. But on the strain tensor, we have strain just in one direction, and there are no strains in the other two. So in this case, notice we have stresses on the 3 directions, but we just have strain in one direction. If you remember the test that we did before to measure the Young modulus, we just had stress on one direction, but if we let the solid expand in the other 2 directions, we have strains in 3 directions, right? So if this is unconfined, different to the one I have over here, I could have a stress tensor which is say sigma 1, 0, 0, and strain tensor, which is, can you tell me what is the strain tensor going to be as a function of sigma 1, 1? It's going to be sigma 1, 1. This one, epsilon 1, 1 is going to be, I know you know these guys, divided by the Young modulus, right? And what about the strains to the sides? It's going to be 0. This is going to be minus Poisson ratio divided by E, sigma 1, 1, minus Poisson ratio, sigma 1, 1, divided by E. So now it's the opposite. You see, you have stress just in one direction, strains in the other two. That's the effect of the Poisson ratio. Okay, so we're good with this problem? Yes?
We did our homework based on the matrix they put in class.
Yes.
Does that mean that affect your grade on the homework?
Um,
Because if the numbers are wrong, the class knows what needs the class needs to do with homework.
I'll talk to the TA. I'll talk to the TA just to consider that that you got to, that there was an error there. Okay? If you don't see that change soon, send me an email to remind me that.
So with that problem, where
Yes.
you let it swing in two directions,
Yeah.
is that called unconfined?
That was, yes, that would be called unconfined. Yeah, because you have no stresses on the sides, or you have constant stresses, which is the same. This is what you did in the lab, right? In the lab, you did this type of experiment. You just apply stress on one direction, and you let it expand in the other two with no stresses on the side. Okay, and the last one, it's more of an application example. And we use the same theory that we have used before, but now we want to calculate horizontal stresses in the subsurface. And in this case, you know what is the total depth, you know what is the Poisson ratio, so you follow the procedure that we laid out some time ago. So I'm going to put the procedure here on the left, and I'm going to go through the homework. First step, you determine vertical stress, right? You know the gradient of stress, you know the depth, you know the vertical stress, the total vertical stress. Second, you determine what is the pore pressure. The pore pressure, in this case, in this particular point, it tells you to assume that there is hydrostatic pore pressure. It's an assumption, okay? It may not be necessarily true, but you are asked to do that, to assume that. So pore pressure, then again, is going to be simply a gradient times the depth, and you get the pore pressure. Third step, you calculate vertical stress. So vertical stress, effective vertical stress, is going to be simply total vertical stress minus the pore pressure. And the fourth step is using elasticity, and in this assumption, if there are no tectonic strains, you just have this very simple equation that you multiply the lateral stress coefficient times the effective vertical stress, and you get a horizontal stress, effective horizontal stress. Then you add that effective horizontal stress. Here you have just the tensor, but you add that to the pore pressure, which is over here. Remember, you add pore pressure just in the diagonal terms to the normal stresses, and you get the total stresses. Total horizontal stress, total vertical stress, which of course should be the value that you calculated at the very beginning. It's the same procedure always, okay? Let's go to the last case. In the last one, you have to relax this assumption of no tectonic strains. So if there are no tectonic strains, so look at this equation. If there are no tectonic strains, that means that your equation is just that. And these two are the same. If there are tectonic strains, you need to consider these 4 additional terms. Okay, the tectonic strains, what they're going to do is they're going to increase the horizontal stresses. And if we now continue the problem, now you have a more realistic assumption of a pore pressure. In the Barnett Shale, as in this case, the pore pressure is not hydrostatic; it's higher than that. So if you know what is the parameter of overpressure, then just simply you calculate. Let me come back to the procedure here. If you know what is lambda p, you calculate pore pressure by multiplying lambda p times SV, and you get the pore pressure. Once you get the pore pressure, you calculate effective vertical stress. Once you calculate effective vertical stress, you use this equation together with the tectonic strains that you know, and you get what are the maximum effective horizontal stress and minimum effective horizontal stress. Notice that here, in order to get sigma H max, you need to use the maximum tectonic strain here in this term, and the minimum here where the Poisson ratio goes. Yes, Ms. Montero.
If you have no tectonic strains, you just have one horizontal effective stress, you don't have like the maximum end.
Correct. Yes. Those will be equal. There will be no reason for those to be different. But if you have tectonic strains which are different in 2 directions, that will give you different stresses too. And that's actually the case in most sedimentary basins. Usually those are different by a bit, by a lot. It depends on the actual condition, but those are going to be usually different. So notice I have broken this stress in 2 parts. The effective stress part from vertical stress. This is just a Poisson ratio, this part, and this is the part of the tectonic strain. You add those 2 up, and then you get the solution, and you add pore pressure to those, and you get the total stresses. You may not have exactly the same values, but don't worry about that. I realized that when I was solving this equation, I rounded up this number with 2 decimals off, so it's actually 34.5. So if you get slightly different numbers, don't worry. If you solve this problem in PSI, I have the solution of that also in my notes. It's right over here. So, okay, these are the equations. And, well, Mr. Campbell, no, what's your last name? Boswell. I'm going to let you go this time with those points about having my equations wrong in lecture, okay? I think that makes sense. Yeah. But you should read the lecture notes, okay? The lecture notes are right. There are almost no errors there. And if you have read the lecture notes, you would have realized that there was a mistake there in the notes. So I encourage you to read the notes, and you will see that you will find almost no mistakes there. If there are mistakes there, so of course I'll take that into account. But here in the notes, I have exactly the same exercise, okay? The exercise of the Barnett Shale, same tectonic strains, saying in modulus, and now I'm solving it in terms of PSI. Here you have all the solutions step by step, and I even have, I don't know if I show you these guys, but I have over here an interactive plot of stresses, horizontal stresses as a function of tectonic strains, which I like that we go through that very quickly, but this is the end of homework number 2. So for homework number 2, you need to know about strain and stresses, about stress and strain tensor. You need to be familiarized with linear elasticity and that stiffness and compliance matrices, and how they are used in order to compute horizontal stresses. And you need to know very well how to compute horizontal stress with elasticity. That's what you have to know, okay, for that part. Any question about homework number 2 before we go into this animation? No? Any complaints about the videos? Yes, I haven't seen many views in my videos, guys. You're not watching the videos. But that's fine. I mean, if you're following the lectures, if you don't need to watch the videos, that's good. But remember that if you miss the lecture, they are there. Yes?
It's actually going to stay if we could go on homework 3 a little bit because it's
About
just like
homework number 3?
yeah.
Yeah, but we need to go first through the theory of that. Okay? So we're gonna go 30 minutes through the theory, and then we're gonna go into the homework. I'm gonna explain how to solve it. So I'll come back to this later on, okay? Because usually it takes time to build. All right, so we are done with homework number 2, and we're almost done with elasticity. So okay, we have still something pending here that I thought I'll have more time for that, but probably I won't. But remember, we're gonna talk about this on Thursday. That real rocks are actually anisotropic, they have plastic strains, and they can be viscoelastic, okay? We'll talk about this on Thursday. I just want to make sure that you know how to solve the homework. And after we do this, then we move into the failure of rocks. So you already know what is tensile strength. Tensile strength is the resistance, maximum resistance of a rock to support a tensile